Okay, this is the pre-calc 1.1 through 1.2 practice test. I want to go over some of the concepts and give you a chance to check all your answers out. First off, the front portion, I'm not going to display that, but basically I think the best way to tackle that is start with the equations and throw those equations in the calculator one at a time and kind of see what table it matches up with. And then with the graphs, of course, you should be able to tell that the E and F are the rational functions. Um, if you're looking at the graph there, I can see E has the asymptote up at 2, and F has the asymptote at 0, so you can kind of tell the difference on those two. And then G you can tell is the quadratic, and the H is the radical function just by the shape. So just answers on those: number 1, the equation is D, the graph is H. The number 2 equation is A, and the graph is E. Okay, number 3, the equation is B, and that graph goes with F. And then number 4, the equation is C, and that is graph G. Okay, so those are your answers to that portion. The second part here was solving an equation kind of graphically and algebraically. So what I would do, if you take a look at number 5, they give you x squared plus 3x plus 2 equals 2x squared minus 6x minus 8. And you kind of have some options. Basically, you should recognize at this point that it's a quadratic equation. We need to set those equal to 0 if we're going to solve them algebraically. So it's just a matter of deciding which side you want to be 0. And I would always try and go to the side where x squared is going to be positive. So I'm going to move all this stuff to the right side. Especially if you're doing factoring, you don't want to have a negative x squared. Now with quadratic formula, it would work out fine, but let's see what happens. Maybe we can factor this thing. Okay, so if we want to get everything to the right side here, again, as long as either side of the equation is 0, we're good. So if I subtract the x squared over from both sides, minus the x, or I'm sorry, the 3x on both sides, and then of course do the minus the 2, we will end up with the big 0 over here, and then we'll get x squared. Those combine to minus 9x and minus 10. Okay, and then the reason I did it that way is because I think factoring is a lot quicker, and in this case we actually can factor. There are factors of negative 10 that add up to negative 9, and those factors would be a negative 10 and a plus 1. So x minus 10, x plus 1. And then we can simply set each factor equal to 0. Okay, that's why we went and got the whole thing set equal to 0 to begin with. Now we can use the zero product property. Okay, that says if two things are multiplied together, okay, this times this equals 0, so one of the two has to be 0. And we can solve that by one little less step there and get our two answers that way. Okay, now the number 6 here, solve an equation graphically. Still a quadratic equation, but we're just going to use a little bit different method to solve it. So that one, what I would do is go ahead and, there's a couple ways actually to do this one too. You can graph the way we did in class, which was graph two separate things, like throw this part into y1 and throw this part into y2, and then look for where they intersect. Okay, so that's fine. Or what I've seen some people do is actually do something similar and get one side equal to 0. So if you subtracted the things over to the right side, you could get something like this, and you would get a quadratic, something like that. And again, in that case, now that you set it equal to 0, in that case, you're now looking for the x values of the zeros. Okay, and the third way even was, what if we would have put everything to the left side? So if we subtract the x squared over, okay, I saw some people do it this way, and that's going to work too. You're just going to get a graph opening downward, but what you'll find is it actually is going to go through the same two zeros as the other version. Okay, so the initial way that I was saying over here, if you just graphed the two things, here's the x squared portion, the 5x plus 10 is just something like this, and they end up crossing twice. And you'd use the intersect command there and there. And the two x values you should get no matter which method you choose. X was around negative 1.53. Okay, and I'm just reading, I know this says negative, or to the nearest thousandth. So give me another decimal there. I don't have it in my calculator, but just to get the full rounding correct. We should carry 3 decimal places and then 6.53 something. Again, I didn't write that down, but you can verify those answers that way. Okay. Okay, then on the table now. Okay, there's a ton of information on here. I'm going to go through all 4, kind of the whole deal. Okay, so 7, the equation they gave us is y equals x minus 3 over x squared minus 2x minus 3. Okay, so what I would do if I were you guys, I'd get a little sketch of the graph, have that off to the side so you can use that. And I believe in this one there was, let's kind of talk about why this happens. You know, the denominator looks factorable, so that's going to be a good start. If we go x minus 3 times x plus 1, that's going to help us see which values are not in the domain. Okay, so the domain, again, anything, they're asking what can you plug in for x. So in a rational function like this with a fraction, you can never have a 0 in the denominator. So your domain is going to be anything as long as it doesn't make the denominator 0. So for this case, the denominator would be 0 if x were 3 or if x were negative 1. Okay, so let me put the slashes through there because actually x cannot be those two things. X can be anything else. So what we end up doing when we want to write that in interval notation, if you think of just a number line here, we can't be negative 1, we can't be 3, but I could put in any number smaller, any number in between, or any number bigger than 3. Okay, there's only 2 possibilities that will give you any sort of problem. Okay, and those are what we found. Those are the only things that make the denominator 0. So to write the domain in interval notation, which is the way we want to do that, we have to show it as everything from negative infinity to negative 1. Okay, so that's this portion right here, along with everything in between negative 1 and 3, okay, right here. And then also, it could be any number bigger than 3, so union 3 to infinity. So that's your domain. Okay, now if you had the graph sketched, you would notice that it does something like something like this, something like this. Okay, and there's actually like a line going through here. Okay, that is our vertical asymptote. Okay, so we'll get to that in 1 second. Let's kind of try and go in order. Next thing on the table was the range. Okay, the range on these is basically asking what y values does the graph go through. Okay, and I think the best way to find the range, if you have this graph in front of you, it's kind of hard to tell. You might see something's going on, but what I would do actually for the rational functions is I would find the horizontal asymptote first. Okay, because that's going to tell you a lot about the range. So in this case, or in any case with a rational function, horizontal asymptotes, you look at the degree here. Okay, the denominator has a larger degree. So when that happens, we get a horizontal asymptote at 0. Okay, so at y equals 0, we have a horizontal asymptote. So you can fill in that box. And on the graph, you should be able to see that. That's this line here. That this graph is actually just approaching, getting closer and closer to, but it's never going to quite get there. Okay, and that tells us all we need to know about the range, actually. Okay, the range, we will go through every negative value. We will go through every big positive value. We just will never go through 0. So the range is going to be everything except 0. Okay, so we're going to write that as an interval also. The range is going to be everything from negative infinity to 0 or bigger than 0. Okay, and I'm using parentheses on the zeros because I never quite equal 0. We'll see one in a second where it equals 0. Okay, so that's that. We did the domain, we did the range. Vertical asymptote. Okay, here's the deal. I'm going to go back to my original function. You can kind of see in the graph here, the green dotted line, that's the vertical asymptote. That occurs right here, okay, when x equals negative 1. And that was, if you notice, the factor that did not get canceled out. Okay, because back in the original function, the x minus 3's can get canceled out. So this value of 3, it's still not in the domain, but it's specifically, it's a hole in the graph. Okay, so let's get our, where are we at here? Our vertical asymptote, again, we said was x equals -1. Okay, because it made the denominator 0 and it did not get canceled out. Okay, we talked about horizontal asymptote being at 0. Okay, end behavior, that also goes with the horizontal asymptote. Okay, if you think about the picture of the graph on the ends, that's exactly what the horizontal asymptote is there to tell us. It's the graph is approaching that on both ends. So what we do for end behavior is we're going to say as x approaches infinity, okay, which means as we go to the right. Okay, so on the graph again, that's this portion up here. Okay, the y values are approaching the asymptote of 0. So the f of x is approaching 0. And you'll notice on the other side of the graph, it's doing the same thing. Okay, if we were to look on the left end, the f of x is also going to 0. Okay, and that's your end behavior. So for any rational function, it's going to go towards whatever the horizontal asymptote is. Okay, we talked about the continuity. Okay, the continuity is basically just stating that we had the vertical asymptote, and then we also had a hole at negative, or at 3, I mean. So when we actually graph this, if we want to do like a more accurate graph, we would need to make sure that we put a hole in at x equals 3. Okay, but again, I'm not grading the sketch. We'll get more into that later. Okay, max and mins. If we talk about increase, decrease first, let's come back to that. So the row right below, this thing is actually always decreasing. Okay, if you follow from left to right and look at what the y values are doing, they're getting smaller and smaller and smaller. So this thing's always decreasing. So what that means is it doesn't have a max or min. Okay, you can see it's going down to infinity. At some point, it's going up to infinity. So there's no max or min on this graph. So you have to write none. You can't just say 0 or anything because that makes me think that there is one at 0. So write none. And then for the increasing, decreasing part, we showed it is decreasing all the time. So you can say it's decreasing, but just remember there are some spots where it's not doing anything. Okay, there were 2 discontinuities at the very beginning. So it's decreasing, and in the shortcut I would just say it's decreasing over the whole domain. Okay, and as long as you have your domain correct at the beginning, that way you just don't have to rewrite it. Okay, but it would be decreasing over the how we wrote the domain up here. Okay. And then the symmetry, even, odd, neither. If you were to pull up a table of values, you would see this one has neither. Again, looking at values on the right and left side of the y-axis, you're not going to have any sort of pattern there. Okay, so more on that in a second. Okay, number 8. This one's a radical function. Y equals the square root of x minus 2. Okay, so again, to get a little visual going, you can use your calculator and verify, but it's going to start here. It's going to look like one of those things. Okay, so in this case, the domain, again, is what x values can you use? So we don't have a fraction, so I don't have a denominator to worry about, but I do have a radical symbol, and the rule for that is whatever you're taking the square root of has to be bigger than or equal to 0. Okay, otherwise you're not going to get a real answer out. Okay, if x minus 2 is a negative number, we're not going to get an answer out. And hopefully you can see how this matches up with the graph if you just solve that for x. Interval notation says anything from 2 to infinity is your domain. And you can see this thing starts at an x value 2 and it's going through everything, x values. Okay, and that's why. That's why there's no point at when x is 1, okay, or when x is 0. It would cause you to have a negative number under the square root. Okay, I think the easiest way to do range on these, there's no really asymptotes to worry about getting in the way, but what you need to do is look at where this thing starts. Okay, so if you want to go to a table or something and get that y value there, and just see that this thing is just, it's increasing from there. So the y values start at 0, it does equal 0, and it goes up to infinity. Okay, it's gradually getting higher and higher. Okay, no asymptotes for these. Again, only the rational functions will have asymptotes for now. So let's go none. So make sure you write that. Okay, end behavior. Again, there's no asymptote, so let's see what it's doing on the end. It looks like this thing's growing and growing. And it's growing slowly, but it is still growing. So for as far as end behavior, it looks like on the right end, so as x gets big, the y values are also getting big. And this is a kind of a special case because there is no other end, okay? Because this thing just like stops right there. There's no left end. So you just have the one end. The continuity, again, we have the domain listed. There's no asymptotes to worry about. There's no issue. You could draw this one by just starting and not having to pick up your pencil. You could draw the entire graph. So this thing has no discontinuities. Okay, max and min now, this one does have. It does have a lowest point that it ever gets to, and that's when it first starts. Okay, so it has a maximum, I'm sorry, it has a minimum of 0. And that occurs at or when x equals 2. So that's what I need. I don't want a coordinate, I don't want 2, 0. The minimum is 0. Okay, that's the lowest this graph ever gets. It just happens to occur when x equals 2. Okay, increasing, decreasing. This thing, if you look at where it starts, and it's always increasing. So you could say it is increasing over the domain. Okay, so it's increasing over that whole domain of 2 to infinity. And symmetry, again, this thing doesn't have anything on the other side of the y-axis. You could pull up the table like we did in class. This thing doesn't have even or odd, so it's neither for symmetry. Okay, and we'll talk about how to prove it in a couple minutes here. Okay, I'm just going to read off the answers to number 9. It's similar to number 7 in that it's a rational function. I guess I'll start a little bit of it, but I don't want to do the entire detail because again, it's just like number 7. But basically, the important differences are the domain will just include all numbers except anything that makes that 0. So I'll pull that out to the side, and I'll see that x cannot be 2. Okay, so my domain's everything less than 2, along with everything from 2 and up. That's my domain. Okay, I only worry about the denominator for domain. Okay, I just know that it cannot be 0. Now, as far as the range goes, okay, in this case, again, before I do the range, you're going to want to know what the horizontal asymptote is. Look at the degrees of each. Okay, that's a 4, that's a 1. So we're going to use the coefficients when the degrees are the same. So there's a horizontal asymptote at y equals 4. Okay, so you'll be able to see on your graph, it does something like this. We got the vertical asymptote from the not being in the domain. And this graph kind of does one of these deals. Okay, so the range on this one, okay, again, there's an asymptote at 4, so it's never going to go through that y value, but it does go through everything else. So it goes everything smaller than 4, along with everything bigger than 4, not including 4 for the range. Okay, we talked about the asymptote. Here's your vertical asymptote because it did not get canceled out. Horizontal asymptote we got. So end behavior again then, I'm going to do this one a little quicker. If you just look at what the graph's doing as it goes to the left and to the right, it's approaching that asymptote. So both ends are going to 4. Okay, so make sure you write those out. The discontinuities, this was our only issue, was that vertical asymptote from the beginning at x equals 2. Like number 7, this one does not have any max or min because it's always decreasing. So no max, no min. It's decreasing over the whole interval, the whole domain, I should say, and then symmetry again is neither. Okay, because it's not the same on both sides of the y-axis or on both sides of the origin. Okay, and number 10, a different type of function, a quadratic. Okay, so y equals 3x squared. Okay, so we should know what that one looks like. You shouldn't even need a calculator. Okay, it's opening upward right through the origin. Okay, and that should tell you some things about the domain and range right away. Okay, so for the domain, again, there's no radical symbol in this. There's no denominator. There's really nothing that would cause a problem. You can take any number you want, square it, and times it by 3. You're going to get an answer out. Okay, so there's no issues at all with the domain. It's all real numbers. Now the range on this one, it does not go through all y values. There is a point there, there's a minimum that it hits, and then it goes through everything above that. Okay, so again, this one I know goes through, or it has a vertex at 0, 0. So the range, it does equal 0 at some point, the y value does, and it only goes up from there. Okay. Again, no asymptotes of any kind in a quadratic. Only the rationals have those for now. End behavior, you should be able to recognize this end's going up to infinity and this end's going up to infinity. So we can write both of those. Okay, there's my right end. And then the left end is as x goes to negative infinity. That y value is also going to infinity. Okay, no issues as far as continuity, because again, the domain's all real numbers, so there is no discontinuity. Okay, max and min. Quadratics definitely have one of those. This one has a minimum, because it opens upward. It has a minimum of 0, and that happens to occur at x equals 0. Okay, and you can see from the vertex there. All right, now increasing, decreasing is slightly different on this one. As we read from left to right, it's decreasing, and then once it hits that vertex, then it starts to increase. So we need to mention both of those. Okay, so this thing is decreasing, and you need to tell me over what interval. So over which x values. So it's decreasing all the way from negative infinity until it gets to 0. Okay, that's when we get to the vertex. Then when you're at 0, it's not doing anything. It's like hit rock bottom. But then it starts to increase from 0 to infinity. Again, those are x values. It's an interval of x now, of the x's. Okay, so that's the interval that it's doing that. Now this one does have even symmetry. Okay, and here's how you can tell. If you were to go to the table of values, let's just put a couple in here. Okay, again, I know 0 goes through 0. If I were to plug 1 in there, 1 squared is 1, but when you times it by 3, it becomes 3. But if I were to put negative 1 in there, negative 1 squared is also 1. When I times it by 3, I'm going to get 3. Okay, and then for 2, if I take 2 and square it, I get 4. And when I times that by 3, I'm going to get 12. Okay, and you should notice the same thing happens up there. So what I suggested was just kind of look for those to be matching up, and as we were to continue, if they all match up, that's guaranteed to be even. So this looks like it's even, and it is, but to actually prove it for like number 11, here's what we need to do. To prove that it's even, I should say proof of even, so not prove. What we need to do is we need to show that that's going to work for every single x value. Okay, not just the few that we happen to be able to see in our table. So what we do is we say, you know, again, here's a picture of our graph. Okay, I need to show that if I were to take some point here, so it has some x value and then f of x, whatever the y value happens to be. I need to show that if I were to go on the other side of the graph, out to the negative coordinate, I need to show that that y value would be the same y value as it was on the other side. So this and this are the same, and that guarantees that it's the same height, it's symmetric over the y-axis. So again, for our example, they gave us the equation f of x equals 3x squared. Okay, what you need to do to prove this is you need to basically show that this side is going to happen. So you always start out by saying, okay, what is f of negative x? And let's see what it turns out to be. Okay, so f of negative x, again, if that x goes right there, it's going to be 3 times negative x squared. Okay, and I'm just going to do a little algebra on that. Negative, if you think about negative 1x squared, when you times it by itself, it just becomes a positive x squared. Okay, and then of course the 3 just gets brought down. And what do you notice? Okay, that was what we started with. That was f of x. Okay, so we showed that it's going to be the same as the y value was on the right side of the equation. Okay, and if you've done that, I've shown that that'll work for any x I want. If I put the negative in, I'm going to get the same y value as if I would have put the positive in. That's how you get that even symmetry, and this proves it. Okay, so you might be saying, what happens if it's neither? What's going to happen? So let's look at one like number 9 there, if I want to prove that. Okay, so let's say we want to prove f of x equals 4x plus 1 over x minus 2. And is it even? Is it odd? Is it neither? And we'll just do this without even graphing it. And of course, you can use your table, and I encourage you to do that. But to do the actual proof, you're always going to say, all right, what is f of the opposite of x going to give me? Okay, so I'm going to go in and substitute negative x's in for both of those. And then you're going to do some algebra and see what happens. Okay, so the numerator is going to be negative 4x plus 1. The denominator is negative x minus 2. And you're going to ask yourself, is that exactly the same thing as what you started with? Okay, does that equal this? Clearly it does not. Okay, so it's not even. Okay. Is it the exact opposite of what we started with? Is every single sign the opposite of what we started with? No, it's not. Okay, we have a negative 4x, but then we have a plus 1, so it's not the exact opposite either. So this thing actually has neither symmetry. Okay, it's just some random point. Okay, so let me just give a couple tips that might just help on the table, just some general guidelines here about domains really quick. Okay, if the function's linear or quadratic, chances are the domain's going to be all real numbers. Okay, if it's a radical function, you need to set, if it's the square root of something under here, you need to set whatever's under there greater than or equal to 0 and solve it to get your domain. Okay, and if it's a rational with a fraction, to get the domain, let's say you have something over something else, you need to just take the denominator and figure out what would make it 0, and those things would be out of your domain. Okay, and then as far as ranges, you're looking at graphs. You're looking at if there are asymptotes for the rational equations, if there's a horizontal asymptote, and that should help you get the range there. All right, so hopefully that helped a little bit. I know it's a ton of information, but just keep working at it, and it'll keep getting better and better.